Alright everyone, welcome back. This is Math 155. Today we will be talking about the sigma summation, we will be talking about Riemann sums, and we will be talking about the antiderivative, otherwise known as the integral. We'll spend most of our time in this class talking about the indefinite integral, as you'll do plenty of definite integration in Calculus 2 and Calculus 2 Lab. Now, without further ado, we're going to get started. So the first question we have in problem number 1 is to write this following sum, 10 plus 20 plus 30, all the way up to 1010 in sigma notation. Then use maple to evaluate the sum. Now we have two ways of writing this in sigma notation. We could use the expressions tab and use the sigma symbol here, or we could use the sum command. I'm going to refrain to using just the sum command because sometimes the sigma summation could run into a little bit of glitches when you use this symbol. Without further ado, the command is sum, stands for sum. For example, if I wanted to sum the numbers from 1 through 10, meaning if I wanted to do 1 plus 2 plus 3 plus 4 all the way up to 10, then I could do x such that x equals 1 all the way to 10. So here, the first argument that I pass into this formula is the rule that I'm doing. So since I'm not doing anything to these values, I'm just adding them. I'm just putting x. So that means that x is going to take the value of 1, then 2, then 3. There's no changing these values. And then it's going to do this sum up to 10. It's going to start at 1, it's going to end at 10. I could have begun this at 0 as well. And at least for this problem, they wouldn't have been any different because this is just the identity. I'm not changing anything. We'll start at 1. So when I press enter now, I should have the value of this particular sum. And we get 55 as the value of the sum. Now I could have used the sum symbol, the sigma symbol, and all I would have needed to do is just change the value here. So I could, use x again. I could use I. The variable really doesn't matter so long as you make the appropriate changes. So if you change the index variable, then you have to change your variables for the rule and vice versa. So I could have done this as well, and notice that we have the exact same value for the symbol or with the command sum. So now that we have the preliminaries out of the way, let's work a little bit with this problem. So if you notice, the first value is 10, the second value is 20, the third value is 30. So it looks like these values are increasing by tens. Now, if you also notice, if I multiply 10 times 1, I get 10. If I multiply 2 times 10, I get 20. If I multiply 3 times 10, I get 30. So I notice that I'm ending at 1010, and that the pattern seems to be that I'm increasing by tens. So this all look like they are multiples of 10. So how do I figure out what value am I multiplying 10 by to get to 1010? Well, we simply divide 1010 by 10. So we divide 1010 by 10, and we get 101. So now we have that this particular sum is simply 10 times x, such that x is going from 1 to 101. Why? Because if you were to plug in 1 for x, and then 2 for x, and then 3 for x, all the way to 101, you will get precisely all of the values in the sum. Once I press enter, we will see what the result of the actual sum is. So if you were to actually sit down and add up all of these values up to 1010, you will get this particular value, 51,510. So that is all that you really have to do for this particular problem. You have to figure out what the pattern is, figure out what the starting value should be, what the ending value should be, and then practice writing things in sigma notation and actually calculate the sum. So I could have done it again using the symbol. I'm ending at 101. I'm going to call this 10I. Let's get that F out of there. And then we are beginning at 1. So we're beginning at 1. And again, we have 51,510. Now for problem 1b, we have write 7 plus 8 plus 9 all the way to 20 in sigma notation. Then use maple to evaluate the sum. So this is not a difficult problem. There's nothing changing here. If you notice, they're all increasing by ones. So what can we do here? Well, here we have a sum that begins at 7, right? Begins at 7, but nothing is changing about the values in relationship to one another, just increasing by ones. So again, we could simply just use the identity. In this case, I'll call it I. So I don't want to change my index. I notice that it ends at 20, and it begins at 7 this time, not at 1. So I'm beginning the sum at 7, and I'm stopping at 20. Once I press enter, I should have the result of actually doing this sum. And we have 189. So if you were to actually sit down and do 7 plus 8 plus 9 plus 10 plus 11 all the way up to 20, then you should get 189. And since we have maple, we might as well just check it. It doesn't take that long to check this work. Just a bit tedious to do, but it doesn't take long. And we have precisely that the sum from 7 all the way to 20 is in fact 189. And just to use the sum command and destroy the dead horse, we have x as x goes from 7 to 20. Again, we pick x because nothing is changing about these values here. If you were to pick up a different pattern, like let's say instead of 8 you had a 14, then 21, and you'll notice that 7 is being multiplied. It's just the multiples of 7. You may have different patterns as well. You may have something like the second number is 15, and the third number is 22, and so on. So then you have a different pattern there. So you have to figure out what this rule is, what the pattern is, and how the numbers are related to one another. Sometimes the pattern is very difficult to find, and that's okay. That's why we are studying mathematics and why we're studying sigma summations. But as we expected, all three values, each way of doing it, will be the same. Now, why is this way not useful for us? Well, because I could give you a sum of, going from, let's say, 1 to 2,000, and doing that by hand could take quite some time. So we have computers to do this for us. We have Maple that could do this for us very quickly. Now for problem 1c, we have to write 7 to the 7 plus 8 to the 8 plus 9 to the 9 all the way up to 15 to the 15th in sigma notation. Then we have to evaluate the sum. Well, if you notice, I'm just taking the base and raising it to itself. In each step, I'm just taking the base and raising it to itself all the way up to 15. Well, if for this sum up here, all I did was write x, then if you notice, I'm simply raising it to itself. Well, to get itself back, I just need to raise it to the x. So that would just be x to the x or I to the I, depending on what index variable you want to use. So let me use the sum, the sigma symbol, and notice that we're ending at 15, not 20 this time. So we're going to go up to 15. We're going to start at 7, And now instead of having I, I'm going to have I to the I. So if we do the sum of I to the I, then the first I is going to be the base, and then we have an I in the exponent. So the first I is 7, so you're going to have 7 to the 7. Then the second I is going to be 8, so you're going to have 8 to the 8, all the way up to 15, which is precisely what we have here in this particular sum. When I press enter, we should have the results of that sum. And you could tell that this is already a very big number. Notice that we only summed about 8 numbers. Sure, we raised them to themselves and then we added them together, but still it's a very large number, considering that this is a finite sum. There are infinite sums. You will learn soon, next semester, or if you next semester for sure, about infinite sums and so on, which are again very, very useful. All right, that's it for problem number 1. For problem number 2, we have to use 3 rectangles to estimate the area underneath the graph of 2x plus 3 equals y, and that is between 0 and 1, between the interval 0 and 1. Now, before we could use Riemann sums in Maple, we have to open up a new package. So if you remember from the work that we did with implicit differentiation, to open a package, we use the with command. So we're going to use with, then we're going to use student, capital S. Then we're going to open up a square bracket and make sure that you write student correctly. Then we're going to open up a square bracket and then capital C, calculus 1. Notice that Maple is going to pre-fill it for you, so all you have to do is press enter and close the parentheses. This package that we just opened will allow us to use all of these commands now. For example, you could use the tangent tutor. We are most interested in the Riemann sum command today, but as if you begin to simply read some of the commands that are here, you should recognize some of the names here, like Newton's method, for example, or the mean value theorem, which you should know by now. So we are now able to use all of these commands by simply calling them. So let's talk a little bit about the Riemann sum command. So by now you should know that a Riemann sum is used to estimate the area under a curve. There are different methods of how to use the Riemann sum, and I'm not going to delve deeply into all of those methods. That's why you have a lecture class for this. However, I will remind you that we can do a Riemann sum with the midpoint of our rectangles inside of or underneath the function that we're trying to estimate the area for. You could use the left endpoints of the intervals, or the right endpoints, or you could use the uppers or the lower values of the intervals as well. So I'm going to show you the midpoint today. I may show you some of the other ones as well, just so you could have an idea of how they look. But without further ado, let's quickly talk about this. So first, I'm going to define my function. So the problem said to use 3 rectangles to estimate the area underneath the graph of 2x plus 3 equals y. So let's call that function f. So f is such that sends values of x, multiplies them by 3. That's what I have here. Multiplies them by 2, actually. And then we add 3. So that is what f is. It's a linear function, so we can expect the graph of it to look like a line with a y-intercept at 3. So we're interested in finding what the area is between the interval 0 to 1. So mostly we're interested in this particular interval right here. So how are we going to do this? Well, we're going to use the Riemann Sum command. So I'm going to use capital R, R-I-E-M-A-N-N, and then capital S, sum. Make sure that you spell this correctly, because if you misspell it, then the command will not work. You should put some respect on my man's Riemann's name. All right, so what do we have? Well, we have our function f of x, and then we are looking at this from x equals 0 to 1, and we're gonna tell Maple what method we're gonna use. So again, we could use the left endpoint, the right endpoint, the midpoint, upper or lower. So I'm going to first show you how the midpoint method will look like. So I'm gonna write method equals midpoint, and then output, you wanna make sure that you do this so we can see a nice picture. I'm gonna use output equals plot, and then we're gonna write partition equals 3. And the reason why I'm writing partition equals 3 is because we were asked to use 3 rectangles to estimate the area. So by writing 3, we are telling Maple to use 3 rectangles to use it to do this estimation. So once I press enter now, I'm going to get a very nice picture telling me showing me exactly how this looks like with the rectangles. And voila. So if you notice, the rectangles the function goes through the top of the rectangle at exactly its midpoint. And this is precisely what we wanted to do, because we cooked up the problem in this particular way. We used the method for the midpoint. Now, using the Riemann command gives us a lot of more information than just a picture. If you notice, we have now a definite integral here of our function f of x, going from 0 to 1. It tells us what actually f of x is, and it tells us that, one, the partition is uniform, and it also gives us an approximate value of what the area is underneath this curve. Now, the area is not really 4, and we can tell because of the holes that we have here. However, we could make this estimation better by simply increasing the number of partitions that we have. For the problem, we are asked to repeat part A with 10 rectangles, and then write this solution in sigma notation. So if you were to manually do the formula, well, first of all, let me actually do this. If you were to manually do the formula, what we'll have is the following. We'll have sum of f of x from x equals 1 to 10. But we're not going to do this because I actually really just want you to play around with the Riemann sum. So I'm going to really just do Riemann sum. And we're going to do again f of x, which I have defined already. I'm going to do this from x equals, again, 0 to 1. And now I'm going to use a different method. I'm going to use method, and I'm going to go with left, and I'm going to keep partition equal to 3. And make sure that you write the output. If you don't write the output, the equals plot, it's not going to graph it for you. And we want that to happen. We want to graph it. Notice now that using the left endpoint of the rectangle, our area estimation actually became lower. And that makes sense because notice all of these empty spaces between the rectangles and the line. So that makes a lot of sense that this will happen. So we have an underestimate of the area underneath this line. When we use the right endpoint, we'll have an overestimate of the area under the line. So if I now change the method to right, notice that I now have an overestimate of this. Now, I did mention that there were two other methods that you could use. Let me just make sure that I didn't mess this up. Good. I think I just zoomed out. Yeah, there's another method that you could use, which is lower. Let me just make sure. Yeah, I think I zoomed out. Let me just zoom in. So method, let me just do this. Method equals lower. Let's go with the lower first. And let me try to zoom in so that you could actually see my screen, because I can't even see it now. There we go. That's better for my eyes. Now notice that the lower and the left actually gave us the same approximation. So we actually got the exact same approximation by using the lower method. And if you do the right method, you're going to get the same approximation. Not the right method, the upper method. You should get the same approximation as the right one. And lo and behold, we do. Now we can move on, and I'm going to use now the midpoint method. But now, instead of 3 rectangles, we're going to use 10 rectangles. And we should in theory get a better approximation of this. So that's one thing that definitely should happen. We should get a better approximation of this. Notice that the approximate area is actually 4, so I take it back. It is actually 4. But notice now that we have many more rectangles appearing in our graph. So if we were to actually use the, let's say, the left or the right endpoint of the rectangle with 10 partitions, it's actually going to get closer to 4, or it should get closer to 4, because it's going to be a better approximation of the area. So notice that now if I use the left one, it became 3.9. That's pretty darn close with only using 10 rectangles. If I increase the rectangle, let's say to 100, well, notice now how small those rectangles are, and notice that the actual approximation is not correct. It's a 4. So we use the correct amount of rectangles needed to get the correct approximation. Now the question that I have is, what will be the optimal number of rectangles? Notice that if we use 60, we are not quite there. We're almost there, not quite there. So, this is something that is pretty nice to look at. If now we use 70, we are a little bit above. So it's pretty interesting to see when you play around with this, what the area come up as. So that is problem number 2b. Now, if you wanted to write your solution in sigma notation, then you have to be a little bit careful, because it's not just writing sigma. If you recall from your lecture, the Riemann sum has another portion attached to it, and it's namely that you multiply by 1 over b minus a. So to answer that portion, I'm going to leave it as an exercise, because that definitely will use some of the things that you should have learned in your lecture. And that takes care of problem number 2. Now for problem number 3, we have to use 7 rectangles to estimate the area underneath the graph of y equals x to the 8 plus 2 on the closed interval 0 to 5. So now notice that we have a closed interval. So we're going to work on the closed interval from 0 to 5. So the first thing that I'm going to do is I'm going to define this function. So that's x to the 8 plus 2. So let's define that. Let's call that G. So we have that x to the 8 plus 2 is G. So now we have a function. Let's look at our function G to see how it will look. Obviously, it's not going to be linear. The endpoints are both going to be going in the same direction up to infinity of both ends, and it's going to have a y-intercept at 0, 2. So let's plot g of x. So we have what it looks like a parabola, at least from afar. So let's zoom in to see how it looks better, how better it will look if we zoom in. So let's go 0, 4. All right, so we have a nice curve from the interval 0, 4. And now we want to go 0, 5 for this, so and then we're gonna use 50 rectangles to find what this area is. So notice that, let me just go up to 5. Notice that here it looks like I'm basically in the on the axis. It looks like I'm on the axis, but we know that that's not the case. We know that, if I zoomed in closer, we're actually not hitting the axis. Like if we go to like 0.000 like 4, for example, you will see that there's a distance between the axis and the y-intercept. So we're not actually hitting it. Whoa. All right. So again, we're going to use the Riemann Sum command. So we're going to use Riemann Sum, and we're going to go g of x from x equals 0 to 5. And now we have, let's go with the midpoint method. And the output equals plot. And then the number of partitions that we said was 7. So 7 partitions. And this is how it looks like with 7 partitions. Obviously, it looks like with 7 partitions, this is way off. I mean, look at all the spaces that we have here. And look at the extra area that we have up here. So it definitely looks like we are off on this sum. Let's try to make that sum better. I think I said 50 rectangles. Yeah, 50. Let's do it with 50. So if we use 50 rectangles instead of 7, we now see that we have a much better approximation. And notice that this number is it's a big number. It's a 10 to the 5 right there. This number looks to be in scientific notation. That Maple is writing in a very weird way. Okay. Now we could get an even better approximation if we used even more rectangles. So let's say instead of 50, we use 700 rectangles. Now notice how nice this looks. And notice, let's see the difference between the approximation. So this is a much better approximation, but we could say that this is 2.17 approximately times 10 to the 5, let's say. The value of the area here. And that makes sense because if you notice, this right here is like 30,000. So it's definitely a huge number once you add up everything here. All of the little areas in here. And that, my friends, is Riemann sum. Those are Riemann sums. Riemann sums are very nice. I really like them. I remember the first time I learned about Riemann sums, it was very confusing for me. So I can understand if you are confused at first with them. But I think what really helped me out when when learning it is really think about it as just length times width of a bunch of rectangles. That's really what it is. You're just adding up the areas of all of these rectangles. All of them have the same width. All of them have the same width. The only difference is the height of the rectangle. That is really the difference here. The height of each rectangle is different, but the width is the same. And that's what allows us to pull out that constant width from the Riemann sum and write it outside of the sigma symbol, because it's not affected by the actual sum. It's a factor throughout. Now for the last problem, we have to find the antiderivative of the function. In this case is sine to the 7x times cosine square of x, and then we have to find the integral of the function given by ln of x raised to this x raised to the 5 times 3e raised to the 6. So for this problem, we're going to do the following. First, I'm going to define the actual function. So I have one of them, I think, was sine 7 times cosine of 2. Yeah, sine 7 times cosine of 2. And I actually wrote in math mode to make my life easier. So I have, let's call that A. So A is sine 7x times cosine square of x. So that's A. Now, to use the antiderivative, we can either go to the expressions and use the indefinite integral symbol, or we could use the integration command, which is simply int, int. And I could simply say, take the antiderivative of a of x with respect to x. You have to, much like with the derivative, you have to tell Maple with which variable you are doing anti-differentiation. Once I press enter, we should have what the antiderivative of this is. And notice that this is this by hand, this definitely would not have been the easiest of antiderivatives to solve. If you notice, we have 4 different fractions in terms of sine and cosine. So this definitely would not have been the easiest one to solve. But Maple makes our lives very easy. Now, you could take the derivative of this, and you will see that you will get back to this, say for a constant. That is something that's important that I should pause and mention. Notice that Maple does not add a plus c. From your lecture, you should know that every time we take the derivative of a function, all of the constant values disappear. So that means that something like this, 2x plus 3, if you take the derivative of that, you'll simply get, the derivative will simply be 2. Well, if you take the antiderivative of 2, which is just 2, you're going to get 2x. So the antiderivative of 2 is 2x. But it's not just 2x, it's 2x plus c. Why plus c? Because this derivative is not unique. If you take the derivative of 2x plus 5, for example, that also gives you a derivative of 2. And when you take the antiderivative, you're going to get, again, 2x plus some constant. In this case, the constant was 5. In this case, the constant is 3. So that's why we always add this plus c, because these derivatives are not unique. We always have to account for the constants that we get rid of when we take the derivative. Now, is there a way to get these constants back, meaning the 3 and the 5? Yes, there is, and that's why we use the definite integral. When we use definite integrals, we actually get back what the value of these constants are, and you'll surely learn more about that in your lecture. And if you don't learn about it this semester, then you for sure will learn it next semester in Calculus 2. All right, so let's move on now that we got that little caveat out of the way. For the second problem, actually, let me just go back here just to show you how it's done with this symbol. So if you use the indefinite integration symbol, then I already defined my my function to be a of x, and I'm taking the derivative with respect to x. So notice that I still get back the same solution. Now, for the second problem, we had a nice function. And we had ln of x to the 5 times 3e to the 6. So we have to find the antiderivative of ln of x raised to the power 5 times 3 times e to the power 6. And remember, we're finding this antiderivative with respect to x. So we always tell Maple with respect to which variable we are taking the antiderivative of. And yeah, make sure that you're always using the exponentiation command, ENT. I believe the answer was the same anyway. Let's just try it correctly. So times 3 times exp 6 times of x. Yeah, same solution. So that's fine. And that's how we take indefinite integrals. This is the process of taking indefinite integrals. Now, what if you were, finding the antiderivative of, something like this? Let's say you were asked to find the antiderivative of this parabola, let's say x squared plus 4x minus 5 on the closed interval, let's say minus 2 to 7. If you were asked to do something like this, then you could simply just say int, make sure your math mode, int for integration, and then you could say, well, what's your function? My function in this case is x squared plus 4x minus 5, and I'm taking this derivative on the interval x. And now to do the definite integration, we do equal. So x equals minus 2 to 7. And to get a numeric answer, we could emphasize that on Maple. So we could say numeric to emphasize that we want a numeric answer. And we get that the value will be 162. Now, if you remove this, you'll get the full solution that we expect, which is also 162. And that's all you have to do for definite integration. Again, you could also use this command. So I could have done negative 2 to 7 from the expressions tab, and that is, let me see if I can just copy and paste it. Paste here. And we get, again, 162. So this is very good. This is very good when we do this. So we now have that the area under this particular curve between the interval minus 2 to 7 is 162. That could be feet, inches, centimeters, we didn't specify. Let's just plot that real quickly just to see how that looks, that graph. Now let's go minus 7. So that looks pretty good. That looks pretty good. And again, we could have used also Riemann Sums. There's no hurt in using it. What was I gonna do? Yeah, method equals midpoint output equals plot, and the partition is to 15. Ah, they didn't say a range. X equals -2 to 7. No S in partition. And here we go. So we have a very good approximation by just using 15 partitions of the area beneath this curve on that interval. So that actually is, amazing that we could do this. We could actually do this. That is the end of this lab. Your lab is actually going to be a little bit longer. Namely, I think you have like 4 parts for this, 2 parts for this. For this, you have 5. But it's not any more difficult than what I just did. Thank you for your attention.